Hello, everyone. It's 1 p.m. Eastern, and that means it's time to begin our special CoCoRaHS Weather Talk webinar on the significant weather events of 2021. A very warm welcome to all of you joining us today. I'm your host, meteorologist Henry Regis. Running the technical side of our program is our very own Noah Newman. We're coming to you live from sunny Fort Collins, Colorado. For those of you who are unable to join us for our live broadcast, we're recording today's talk, and it will be available later this week on our website. All of our Weather Talk webinars are sponsored by generous donations by listeners just like you. Well, we're excited to have back with us our good friend Greg Carbin. Greg is the Chief of Forecast Operations for NOAA's NOAA's Weather Prediction Center in College Park, Maryland. Each year, Greg puts together a presentation on the top 10 events in the United States during the past 12 months. Greg has given these talks to packed rooms at various weather meetings across the country, and I've actually seen him do that in person. So, Greg, it's great to have you back with us this year, and we really appreciate taking time out of your busy day to do the webinar.
Well, thanks, Henry. And Noah, let me get my slides up here and we'll get our annual review of meteorological memories over the past year. You should know the rules by now, but just in case, here's a rundown. These are my memories, not necessarily Noah's, although I am on the clock today. And I'll tell you why that is. It's because outreach with CoCoRaHS is incredibly important. And your observations of rainfall and other weather parameters are actually used daily by the Weather Service and by the Weather Prediction Center. So I feel that this is the least I can do to pay off the community out there that's providing real-time observations, especially for precipitation and snow. I don't rank these events. We're going to follow along in generally chronological order. And like almost every year, 2021 was exciting from a storm perspective, but also quite devastating. We'll go over hurricanes, floods, tornadoes, and even wildfires. Each year, I try to fit these into the talk. I'm interested in all extreme weather and try not to be too partial to any particular type or region. That's sometimes a challenge, but this is a labor of love. And so thanks for attending. And here we go. So the cold wave that occurred across the central United States and the southern parts of the US in mid-February has preliminary damage losses in excess of $10 billion. Texas experienced the majority of these losses, with costly impacts occurring in more than a dozen additional states. And this event was the most costly winter storm event on record in the United States in history. Here's a partial timeline of the events. This is really a coast-to-coast storm system, with the greatest impacts being over the southern tier of the United States. Arctic air began to invade this part of the country around February 11th, and at that time, the cold air spread across coastal locations of the Pacific Northwest, where a major ice storm impacted parts of Oregon on the 12th and the 13th. Seattle had its snowiest day since the late 1960s, and that was on the 13th. Back in the plains, Oklahoma City picked up half a foot of snow, and after living there for 20 years, that's pretty unusual. And the high temperatures were even more unusual, not even really getting out of the teens on Valentine's Day. Hundreds of daily low temperature records were set in subsequent days across much of the southern plains, and additional incredible snowfall records occurred from Texas to Arkansas as multiple disturbances tracked across these areas and across that dome of Arctic high pressure that was anchored over the south. The prolonged Arctic air caused widespread power outages in Texas, as well as other parts of southern states, with multiple days of sustained below freezing temperatures. Electrical generation literally froze up, coincident with skyrocketing demand. At the peak of the outages, nearly 10 million people were without power. Additional impacts were frozen water pipes, which burst upon thawing, causing water damage to buildings. And these extreme conditions also caused or contributed to the deaths of nearly 250 people in Texas alone. There are some 24-hour temperature summary maps here that I put together from meso-analysis data grids, basically taking the hourly information, summing it up, dividing by 24. You can see the mean Texas temperature for each day is shown in the upper left. Might be a little bit hard to see here, but what struck me about this analysis was the mean temperature of around 12 degrees for the entire state of Texas on Monday, February 15th. That's just an insanely low mean temperature for such a large state at this latitude, even in February. The chill began to ease by February 20th when the mean temperature across all but the extreme eastern panhandle, as you can see in the lower right of the screen, rose to above freezing in some locations for the first time in 10 days. So this was an incredibly impactful event that we're still talking about and still analyzing. On to number two for 2021, the March 13 and 14 strong blizzard brought heavy snowfall to the Central Rockies and adjacent high plains. Denver measured its fourth largest snowstorm on record, while Cheyenne reported its heaviest multi-day snowstorm on record. And blizzard conditions and heavy snow rates disrupted transportation across this region. You can see the visible satellite image on the left there with the wound up cyclone, a classic comma-shaped cyclone over the western U.S., and then the expansive blizzard warnings and winter storm warnings in effect across this area. There was some talk at one point that the National Weather Service office in Cheyenne may have had to have food dropped to them because of the inability to get in and out, but eventually they were able to dig out from the office there. From the WPC review for this storm, treacherous travel conditions were observed as far west as Arizona on Sunday morning, with several crashes and lane closures due to icy roads. Whiteout conditions and pictures of towering snowdrifts were frequently reported by local TV stations throughout various social media channels. In fact, on the evening of March 14th, the Cheyenne office mentioned that snowdrifts were an astonishing 5 to 10 feet in height. Wind gusts exceeded 50 miles an hour, and snowfall rates of 2 to 3 inches per hour made for zero visibility in blizzard conditions. The Denver International Airport reported just over 27 inches of snow for this storm, making it the fourth largest snowstorm in Denver back to 1881. Farther north, Cheyenne Airport measured 31 inches. About 23 inches of that fell on March 14th, making it Cheyenne's single snowiest day on record. The March snowstorm became the fourth snowiest on record for Scottsbluff, Nebraska, where a 3-day total of 18 inches was reported. The last time that Scottsbluff picked up more than 18 inches of snow in 3 days was April of 1927. And the highest reported snowfall total in Wyoming came in near Windy Peak along the Laramie Range with an incredible 52.5 inches of snow. Surprisingly, you're still measuring at half-inch increments there with 52 inches on the ground. That's pretty surprising. On to the next event, number 3. 2 tornado outbreaks occurred 8 days apart over the south. In Alabama, there were 25 distinct tornadoes that were surveyed after the March 17th outbreak, making it the 6th most prolific tornado outbreak in the state since 1950. About a dozen tornadoes hit very close to the same areas a little over a week later, and this included 4 EF3 tornadoes, 3 EF2s, and 3 EF1s. Damage was significant along the paths of these most intense tornadoes. Unfortunately, injuries and fatalities did occur. And note the similarities in the report locations, especially across Alabama, and the very similar surface maps more than a week apart. The most stunning tornado of the event on the 25th was a long-track 80-mile tornado on the ground for over 98 minutes from Hale County to Shelby County, Alabama. This is the 7th longest single-track tornado in the state history. Another similarity between the two events was the location covered by the Storm Prediction Center's Day 1 high risk. And you can see those two events here. After no high risk areas were issued for any day in 2020, the high risk on March 17th was the first since May of 2019. By the way, that's not the longest span between high risks. That occurred between June 2014 and January 2017 for those of you keeping score at home. This is event number 4, the Tennessee Valley floods, mostly across Tennessee and the Nashville area in late March. And what I'm going to do is run this loop here. Hopefully this will show up on the screen, showing the evolution of the supercell storms and then a large thunderstorm complex bringing heavy rain, essentially near the I-40 area where a warm front had stalled during these days. Between 3 and 4 in the morning, numerous showers and thunderstorms developed along the warm front. Let me start that one more time. developed along the stalled front. Another round of severe thunderstorms, including a few supercells, developed in the afternoon and evening near and south of the warm front. After midnight, even more heavy rainfall along the already waterlogged I-40 corridor prompted rare flash flood emergencies for southern and eastern Nashville. Rainfall between 7 and 9 inches caused rapid rises on several Nashville metro creeks and streams, including 7 Mile Creek, which reached its highest level on record. Many creeks reached their second and third highest water levels ever recorded. The rapid water rises flooded hundreds of homes and businesses, with reports of some people trapped in the attics or on roofs. Dozens of roadways were flooded and impassable, including both I-24 and I-40, with many cars submerged. Although the lowland floodwaters receded quickly on Sunday, March 28th, many rivers later reached flood stage up to a week after the event. 6 deaths were reported, and the flooding across Middle Tennessee is some of the worst since the widespread flash flooding in the same area in 2010. That was in early May of 2010. And here's the radar estimated rainfall on the left and a plot of the flash flood reports across Tennessee for this event. Unfortunately, it appears the Waverly, Tennessee flash flood later in the year may go into the books as the most catastrophic event across this region for flooding. Memory number 5. Well, here are a couple of snapshots of the drought conditions across the contiguous United States from the start of the calendar year to just the end of, well, this was the start of the calendar year to late summer, August 10th, 2021. And while there's been some recent improvement across conditions in the Southwest, overall, the drought has worsened considerably from California to the Northern Rockies. And again, this talk was prepared toward the end of the year. There's probably been additional improvement in some parts of California with the recent precipitation events in that part of the country. Clearly, numerous heat waves across the West have exacerbated the drought conditions in these areas and have also led to some of the worst fire weather conditions and smoke conditions ever experienced in some areas of the West. And this plot shows the long-term time series of the coverage of drought categories across the Western United States. And it's pretty dramatic how the exceptional drought, the most extreme category, has expanded in 2021 and now appears to cover more of the West, at least when this chart was done at the end of last year, probably end of summer. It actually covered more of the West than at any time over the past two decades. The Dixie Fire in Northern California has scorched thousands of acres, making it the second largest fire in the state's history. And fires in the western half of the contiguous United States, including Colorado and Wyoming, have burned on average 30 square miles of total area every day since early June of 2021. An area approaching half the size of Washington, D.C. every day, with the exception of some relief in the Southwest. The situation remained quite dire through the end of the year. And obviously, as we'll see at the end of my talk today, remain quite dire even into portions of Colorado. Memory number 6. I'm kind of deviating from the chronological flow here to hit reverse and look back at June and ask, where did all the SPC tornado watches go? June 2021 was the 3rd year in a row with very few tornado watches during the month of June. In fact, only 10 tornado watches. June 2021 ties with 1998 of June for the 3rd fewest tornado watches on record, approximately 25% of the normal number of tornado watches. Even more interesting is that this is the 3rd year in a row with a record number of low tornado watches. So what's going on here? According to the SPC Daily Tornado Climatology, June tornadoes are typically found roaming around the high plains with a slight extension east across the Corn Belt and Midwest during the summer month, June. In a very crude use of reanalysis data, I decided to run a quick calculation of the change in the wind speeds in upper levels of the atmosphere, about 500 millibars, across the US between the most recent decade and the decade of the 1990s, when some of the most prolific June tornado events occurred. I also looked at the change in temperatures just above the surface, the 700 millibar layer, mid-layer, between the Junes of these decades. In other words, the warmer temperatures aloft could play a role in inhibiting strong thunderstorm development. And weaker winds aloft would certainly inhibit tornado events. So the hypothesis was that we should see some decrease in the mid-level wind speeds and perhaps a slight increase in the temperatures at 700 millibars, meaning a stronger, what we call capping inversion that could inhibit deep moist convection or thunderstorm development. So what did we find when we looked at the reanalysis data for this? This is the NCEP NCAR reanalysis plotter, and I spent a little time here trying to get these plots to make some sense. It does seem as if there have been small changes in these two atmospheric proxies for what we call shear and instability. I'm sure it's likely far more complex than I'm leading you to believe here, but at first look, the capping may be getting a bit stronger as the shear gets weaker across at least some of these areas that tornadoes have been favored in the past. Further review of shifting seasonal centroids for severe weather events, especially tornado events, will be needed before we can say with any confidence there's a trend here. But at least over the last 3 years, tornadoes, or more correctly, tornado watches, have become a rather rare occurrence during the month of June. Number 7, we're moving right along here, so I'll have plenty of time for questions. Also occurring during June, an incredibly hot few days at the end of the month over the Pacific Northwest. Just look at these numbers. The locations shown on the map in Washington and Oregon established new preliminary all-time maximum temperature records for any calendar day. And it's quite remarkable for these temperature records to occur during the month of June. They usually occur in July and August in the past. Even more remarkable that some locations obliterated their previous all-time records by more than 10 degrees. And I think quite incredible that the majority of cases, the prior all-time record maximum temperature had only been set the day earlier. So this is a multi-day heat wave of tremendous proportions, perhaps not experienced in history before. This may be one of the most unusual weather events of the year and was brought about by highly anomalous upper-level high pressure and intense subsidence or sinking air that extended well into Western Canada, where all-time record high temperatures were also established in late June. I played around some more with the mesoscale analysis data and did some of these plots myself, looking at not only were the temperatures incredibly uncomfortable in some regions without a lot of air conditioning, those high temperatures lasted for hours on end in some locations. So this is a look at the number of hours for each day when the mesoscale analysis showed hourly temperatures at or above 100 degrees Fahrenheit. By the third day of the heat wave on June 28th, some parts of interior Washington and northern Oregon were seeing temperatures over 100 degrees last for more than 8 to 12 consecutive hours. That's just incredible and also incredibly deadly. There are estimates of over 500 fatalities over the long term resulting from this heat wave at the end of June. On to memory number 8, two events actually. Tropical storm Claudette produced gusty winds, flash flooding, and tornadoes over much of the southeast U.S. during the 3rd and 4th weeks of June. Impacts were most severe in Alabama and Mississippi, where heavy rains caused flash flooding. And the map on the left depicts the 4-day rainfall from Claudette, which moved north from the Gulf of Mexico as a potential tropical cyclone and made landfall as a weak tropical storm in Louisiana on June 19th. Extreme southern Mississippi recorded up to 11 inches of rainfall, and southeastern Louisiana accumulated more than 9 inches. Several tornadoes were also occurred in the southeast states and caused severe damage, including an EF2 that damaged a school and destroyed parts of a mobile home park in southern Alabama, injuring 20 people. A weakened Claudette continued on an east-northeast track and prompted additional tropical storm watches and warnings from Cape Fear, North Carolina to the Outer Banks. And Claudette regained tropical storm status over northeast North Carolina on the first day of summer, June 21st, before moving over the western Atlantic and weakening. Next came Elsa. Hurricane Elsa was the earliest hurricane in the Caribbean Sea and the earliest forming 5th named storm on record in the Atlantic Ocean, surpassing Edward in 2020. The first hurricane of the 2021 Atlantic hurricane season, Elsa was monitored by the National Hurricane Center as a tropical wave on June 29th, was designated a potential tropical cyclone on the 30th, and Elsa was upgraded to a tropical storm on July 1. On the 2nd of July, Elsa was upgraded to a Category 1 hurricane after undergoing rapid intensification. However, landfall over Cuba reduced Elsa back to a tropical storm on July 5th. Elsa briefly regained hurricane status during the evening hours of July 6th west of Florida and made landfall as a tropical storm near the Florida Big Bend on the 7th. After landfall, Elsa began accelerating northeast and became extratropical on the 9th of July, but not before also producing a stripe of heavier rainfall and strong winds and minor storm surge flooding and several tornadoes from the mid-Atlantic to southern New England. So that was Elsa. Then I kind of had a bit of a break before Ida came along, but here is number 9. And Ida is quite memorable. I worked 14 days in a row during Ida and up to Ida's landfall in Louisiana. And you can see there the landfall in Louisiana. Just basically Grand Isle was the area that took the hit there. And there's an aerial photograph, the post-event aerial surveys of Grand Isle showing the degree of damage with that part of southeast Louisiana. And then the event continued inland as far as a heavy rainfall threat. At this point, personally had a wedding to attend. My younger son was married in Vermont. And so I got a break from my 14 days of working tropical cyclones and took off for Western Vermont, where I saw the most incredible sunset that I've ever seen in my life the night before my son was married. That's Western Vermont, Lake Bomazene there. The sunset being highlighted by the mass amount of moisture streaming north into dry air over Vermont. At about the time that this picture was taken, New York City was undergoing tremendous rainfall, devastating rainfall amounts across parts of the New York City metropolitan area. And I was well aware of that. And even though there was a lot of partying going on for the upcoming wedding to be had in the family, I basically spent the whole night watching radar in disbelief because the rainfall amounts across the New York City area were devastating. And WPC stays quite busy with these events and actually did quite a bit of outreach ahead of it with a day 2 upgrade to a high risk and the excessive rainfall outlook across Pennsylvania, parts of New York City and southern New England. And then the day 1 event unfolded, unfortunately, as forecast, just an incredible rainfall event coinciding with the vulnerability that you have in densely populated urban areas. On to event number 10. How can we not cover this? Record-setting December tornado outbreak with over 60 tornadoes and at least 80 fatalities. This is a nighttime event with Mayfield, Kentucky, taking almost a direct hit by an EF4 tornado, and incredibly long track tornado, especially for the month of December. There were other damages as well as far north into Illinois. And so this one makes number 10 for the year, the December tornado outbreak with devastating consequences there. And then I had to go to 11 this year because it's just so many things going on. And so we'll go to number 11 here, which basically I added this slide just yesterday for 2021. The explosive firestorm called the Marshall Fire erupted just before New Year's and unfortunately took an incredibly devastating toll on a number of neighborhoods between Boulder and Denver, Colorado. I have a lot of friends in that area, some of whom have been impacted by this event. Here is the setup. The Front Range region of Colorado experienced a highly anomalous warm and dry period through the second half of 2021. The chart on the left depicts the average temperature on the y-axis and the accumulated precipitation on the x-axis. And you can see how unusual 2021 has been compared to the past 75 years or so, standing out way out here at the edge of the distribution, just highly warm and dry. And so this warm and dry weather contributed to extreme drought, as shown in the plot in the upper right. And then on December 30th, a downslope windstorm resulted in really low relative humidities and extreme hurricane force winds. All that was needed was a spark. The GOES satellite imagery is used occasionally to highlight areas of rapid warm up at the surface due to wildfire starts. And so here's the GOES image showing the hot spot there just to the southeast of Boulder. It picked up the beginning of the conflagration here on satellite. And then the radar basically showed the plume of smoke emanating from those fires near Louisville and Superior in Colorado. I watched this event through the evening. I talked to a close friend of mine who was evacuated from his neighborhood in Louisville on the phone, and continued to watch in horror as this smoke plume did not dissipate for many hours. I don't know if I've seen a wildfire on radar persist for such a long period of time with such a strong signal. I've watched a lot of wildfires and smoke plumes on radar, and normally they tend to dissipate relatively quick. This went on for hours, and it was, gut wrenching to watch that happen because you knew that that homes were burning in that area. So this shows the interagency damage assessment of the Marshall Fire. Over 6,000 acres burned. This was recently updated, and as a zoom in on the burned area, there were over 1,084 destroyed residences. This was updated just a few days ago. 149 damaged. The total countywide estimated value of residential damage is over $500 million. I'm sure that will go higher. The updated numbers for commercial structures are 7 destroyed and 30 damaged. And they're still calculating the losses out there. And so if there are many opportunities to give in support of recovery out there. The Boulder Community Foundation is one. I know there are a number of GoFundMe sites too set up for folks to try to help them recover from this devastating loss. So that's how we ended 2021. We can certainly hope that 2022 is perhaps less devastating, but I'm sure it will have just as much interesting weather going on. So there's the summary of this memorable year from memory number 1 through memory number 11. And I think we've taken just about half an hour here, and that should leave us plenty of time for questions. So thanks once again to Henry and NOAA for having me here today. I appreciate that.
Greg, we really appreciate you giving this presentation. Yeah, some memorable stuff there. As we look back, I mean, the fires for us, we could actually from Fort Collins see the smoke in the clouds. What was really interesting here, not even a breeze in Fort Collins, and
amazing
south, yeah. And we were over 100 miles an hour. The wind, very dry. Yeah, just a gut wrenching thing to watch, and that close to home. So, yeah, I've got a question for you. Looking at the outbreak in Kentucky with the tornadoes back in December, that long track looks very similar to the tri-state tornado, 1925. Almost, if you shifted, I don't know, 50 or 75 miles southeast, it would almost be an overlay. And I'm just curious, a similar setup or I'm just curious.
A different time of year, right?
Yeah, I mean, right.
So the tri-state was in March, yeah. And it is a really interesting endeavor in meteorology to try to understand what is it about these long track, especially long track intense tornadoes. The parent supercell is obviously in an environment that is non-destructive. Often what you'll see with widespread severe weather is you get into sort of a destructor regime where the outflow from one storm can impact another. And so the storms can still produce tornadoes, but they're intermittent or segmented tracks. And clearly the event of the tri-state tornado is a very intense cyclone, which this one was as well, intensifying cyclone. But I believe there's probably finer scale details that are in the lower levels of the atmosphere. There's something to do with the ability to maintain a very not really wanting to use the word stable, but an unchanging environment for supercell storms to persist and not basically die out or interfere with one another. And so this is one that I think will be definitely looked at closely to try to better understand what is it about these environments that you can sustain robust supercell tornadoes over such an extensive track. And they're not common. And so I would imagine that we will find that the environments in which these occur are also not common.
Okay, thanks a lot. Well, we've got some questions coming in, and let's take some of our questions from our viewers here. Chris writes, "Is any theory to account for the apparently periodicity of severe drought, it seems to drop every 5 to 6 years as you look at your graph on that.
Well, we know that there are obviously large scale oscillations that affect climate and modulate the flow and jet stream pattern. One of the more well known is ENSO, or the El Nino Southern Oscillation, and what the El Nino Southern Oscillation is a good word to focus on there, because the way that changes from a cold region of the Pacific Ocean affecting the large scale jet stream to a warm region also impacts downstream weather. And so what you'll see often during the El Nino is you may see a period of wet weather on the West Coast or across parts of the southern US. And then you flip or oscillate to the dry regime, which not only causes the drought to come on, but now you have a lot of potential fuel for wildfire activity. So you often see that the green up phases occur over several years during one phase of ENSO, and then the drying out occurs over another phase of ENSO, and you see an increase in wildfire activity. Obviously, there's a lot more to it than that, and we're still trying to figure all that out. And of course, on top of all of that, you kind of have to overlay climate change and what's going on there to impact these regimes. And so there's some talk that we may be in a long-term decadal drought across parts of the western U.S. Let's hope that's not the case, but certainly this last year definitely caused some issues and stresses with respect to water use across parts of California and Arizona.
Thanks. And Ken writes in and talking about the tornadoes. He said, December 15th saw those outbreaks and some all-time December high temperatures. What's your impression? Is that any relation? Is that just your impression of that whole event?
Well, December has now come in, I believe, as the warmest December on record from the National Environmental Information folks down in Asheville, focused primarily across the southern U.S. And again, perhaps a feedback mechanism going on there a bit. You saw the drought conditions across parts of that area. Dry ground kind of contributes to this unfortunate feedback cycle where you warm up a lot more effectively without the moisture in the air, and so dry conditions are in effect a precursor perhaps to warmer conditions as well. And then the large-scale jet stream pattern that's set up across this region, with generally what we call ridging maintaining itself across parts of the southern U.S., resulting in those warm temperatures throughout the month of December, and not much of a winter for many areas of the country. I think we've turned the corner a little bit on that now that we're in January, but we'll see how long that lasts.
And similar about the tornadoes, Deirdre from Minnesota writes, she wanted to know about the line of storms in the radar on that event. Long, narrow line. Is that unusual? Is that it looked like it really, like the training as it went across. How usual is something like that?
So there's a number of factors that could have played into that, and in fact may have also contributed to the fact that you were able to maintain separation between some of these storms along that line, to the extent that the supercells didn't interfere with one another, and you result in a long track tornado. Not uncommon. A lot of these events are characterized as what they call quasi-linear. They're sort of like a line. Or squall line, but they've got segments in them, and usually those segments are composed of supercell thunderstorms. So not an uncommon characteristic, perhaps a little more likely to occur in environments that aren't overly moist. If you have a lot of moisture, a lot of instability, and not a lot of what we were talking about earlier about capping or an inversion that keeps thunderstorms suppressed, you tend to develop thunderstorms along where you have your strongest lift or forcing, so ahead of a cold front or along a trough. and then they move basically from west to east. So the characteristic of what the radar looks like is really dependent on the attributes of the air mass, whether it's very unstable, and what kind of forcing you have, and also what kind of shear. So during the cool season, you might expect to see these narrow line segments associated with thunderstorms and severe weather.
Okay. Also, Chris writes in, and this is an interesting question, again, with these tornadoes. He was wondering, does anybody study the interaction of terrain elevation and tornado persistence? So is there something to a correlation there?
There has been some work done on that. There's some peer-reviewed research looking at the frequency of tornado events associated with differences in surface elevation. We know that the higher in elevation you get, you normally don't see the same characteristic of low-level moisture. You don't require perhaps as much what we would say the dew point temperatures, say in the Front Range of Colorado. If you get into the mid 50s there, that's a very conducive environment with the right conditions for severe storms. And so elevation certainly plays a role in weather, and often will play an enhanced role when the wind speeds, or when the wind direction is basically moving what we call upslope, as opposed to downslope. And so elevation certainly does have a factor, and there has been some work done on this. I'm not sure there's anything definitive, but I also know there's been some work done in parts of Alabama where they look at long track tornadoes and their tendency to perhaps follow terrain instead of crossing over terrain. They're following along valleys, but that could also be the way the valleys are oriented southwest to northeast. So there's kind of a tricky chicken and egg question there.
Thanks. Well, here's Rex writes in and wants to know, are there any common themes from a climate perspective with your top 21 weather events? So any themes that pop
That's a
out
great
for you?
That's a really great question. I think what I should do, I may have done this a few years ago, is sort of categorize what kind of events I'm talking about from one year to the next. And again, that's a little tricky because I started these talks when I was working at the Storm Prediction Center, and so there may have been a little bit more focus on severe thunderstorms, tornadoes, and hail, which are all very memorable events when you have them. But I also have focused on floods and tropical storms. Like I said at the beginning, I try not to be too partial to one particular interesting aspect of weather. I love winter storms as well. So I do sense that, if I just off the top of my head, that we are seeing a lot of wildfire impacts from year to year. So wildfires, wildfire events, drought, and heat are certainly showing up just about every year. Now you would think that drought particularly may not be all that entertaining a meteorological memory to talk about, but it certainly played a big role in the past couple of years.
Okay, here's two questions that are interesting that effects of events happening. So Brenda from LaFontaine, Indiana says, I've always wondered if the Port-au-Prince, Haiti earthquake knocked us a little off our earthly axis and had any effect on our weather patterns. And then another one here from Monica, there's been a lot of focus on glacial melt. How do you see this affecting our weather patterns in terms of jet stream positioning and severity of weather? And she's from Thunder Bay in Ontario, Canada.
Oh, I've been to Thunder Bay. Hope you're having a nice winter up there. So as far as the earthquake changes, that's actually probably more of a geography question, certainly earth science related. Don't know, exactly how to. There've certainly been some pretty powerful earthquakes, including the Japan earthquake of March 2011. This is probably as strong, perhaps a little stronger than Haiti. With respect to glacial melt, I think probably the larger impact we're starting to experience there is with sea level change, the rises in sea level, those are having an impact on the frequency of coastal flooding events, both high tide events, but also when you see winds blowing onshore, whether that's from a hurricane or just a strong cyclone like we'll see over the next few days on the East Coast. Those have a tendency now to more frequently result in impacts right in the coastal zone, where you'll see coastal flooding occurring quite easily now with the slightest of onshore winds. The number of coastal flood advisories and warnings, even here in the Washington, D.C. area on the Potomac, on the tidal Potomac, have increased dramatically in recent years. And that's primarily due to sea level rise, which is in part due to melting ice caps. Now, there's also some work I'm not involved in, but you hear the stories and you look at the research that's being done with respect to fresh water entering parts of the circulation, the ocean circulations, and causing changes in ocean circulation that could have an impact on storm tracks as well.
And here's another one with a asking about effects. I didn't see this here. Maggie wants to know: do intense wildfires affect or alter subsequent weather patterns? Do they interfere with the natural circulation? What happens with those?
So that's a great question. I think there are downstream impacts from dense smoke, particulate matter in the atmosphere brought about through wildfires probably play some role in the ability to generate storms or precipitation systems downstream, perhaps downstream from wildfires. You also see impacts in terms of the daily heating cycle. Obviously, a thick, dense pall of smoke will probably prevent it from heating up and cooling down as much at night. So the diurnal temperature cycle is probably impacted as well. Everything's connected, right? So when you generate these massive fires that then create smoke plumes for thousands of miles, there are clearly going to be impacts downstream and connections to those fires that we may not have anticipated.
Yeah, we noticed with the fires out west of us this year, we spent a good part of July and August thick in smoke. The air quality here was just amazingly bad for a long period of time. It just
the health effects.
It definitely. Okay, couple more questions and then we'll wrap it up. But let's see here. Speaking of nighttime, mentioned there a minute ago, Charles is wondering: are nighttime tornadoes occurring more often? Is there a difference in the dynamics of tornadoes at night as compared to daytime ones?
So I'm not aware of any research showing an increase in the tornado activity during the night. There is an interesting hypothesis, you might say, that given that we're seeing warmer temperatures both night and day, and actually we're seeing much more warmth occurring during the cooler time of day. In other words, the temperatures at night are not dropping as low as they might have in the past. That would perhaps support the potential for more severe weather during the nighttime hours. In other words, the warmer the air, the more stability around, the longer you might be able to sustain severe storms into the late evening. However, I've not seen any research or studies with that. What we do know that at night, it's very difficult to see the tornadoes coming, and a lot of folks, regardless of where you are, want to search out that corroborating evidence. If they hear that they're in a tornado warning, normally there's a tendency to want to go check out the sky, which is probably not what you should be doing, especially at night, because you're not going to be able to see it coming. So tornadoes at night, we do know, are particularly dangerous because of the inability to see them coming. And also, often if they're late enough at night, many people are in bed and may not get the warning ahead of time, and that's a good reason to plug NOAA weather radio, where you have the potential to alert for any warning in your area. You set the NOAA weather radio up for your town or county or zone. Actually, in this day and age now, the phone will get the warning too if you're in the cell network, and the polygon that outlines the possible tornado will alert cell phones. So take those warnings seriously all times a day, but especially at night when you can't see them coming.
Yeah, it's interesting living here on the Front Range. We rarely get nocturnal thunderstorms. I mean, having lived back east, and recently I was in Arkansas and parts of Chicago during the fall, and boy, 5 o'clock in the morning, wake
Oh
you right
yeah,
up.
yeah,
It's
yeah,
something
yeah.
you're not used to, and it's tough when they occur that time. To be hard. Okay, a couple more questions here. So let's see. Mike wants to know, you used the term millibars earlier to indicate altitude several times. He wants to know, do millibars relate to the distance above the Earth? What are you talking about there?
So it's a pressure level, just like at so there are various ways of measuring pressure in the atmosphere. Inches of mercury is kind of a standard as well, and altimeter settings are used to measure the basically the amount of air above your head. And so in the atmosphere, as you go up, the pressure is lower, and as you go down in the atmosphere toward the surface, the pressure is naturally higher. Another phrase for millibars is hectopascals. That's a measure of pressure as well, and these pressure layers in the atmosphere change in height. Their height is different. Basically, because the atmosphere acts as if it's a fluid. It is a fluid of air, and so those pressure levels, the constant, what we call constant pressure levels, actually the pressure is constant, but their altitude above our heads is not, because it's like a wave. And so when we say 500 millibars, we're actually talking about a height. It's a pressure, but at what height is that pressure? And by looking at the variability in the height of that pressure level, we can actually visualize the waves in the atmosphere.
Thanks. Here's one from Cindy. We're going to look at the tropical stuff here. The tropical storm season started out with an average number of storms, yet late in the hurricane season, there weren't many. Can you explain what changed between these two periods in this year?
That's a great question. I'm going to be attending some of the national hurricane conferences later in the spring, and maybe I'll have an answer for you at that time. There are a number of factors that play into the genesis of tropical cyclones. One of them is that can suppress tropical cyclone activity, and we saw a number of events throughout the season, is sand and dust that comes off the Sahara in Africa. That can tend to suppress the development. And again, it goes back to the comment earlier about smoke being suppressing temperature variation. So you're not getting as much heating at the surface when you have the dust plumes coming off of Africa. And there were a number of those. So it may have been an increase in the number of dust events across that part of the Atlantic, what they call the main development region. Also, wind shear plays a role. And unlike severe weather for tornadoes and hail, where you want shear in the atmosphere to see that type of development, as a meteorologist, you're looking for shear for severe thunderstorms. As a tropical meteorologist, you're looking for where the shear is weaker, so that the thunderstorms can develop upright and gain organization. So it's possible that the shear across portions of the South Atlantic and the Mid-Atlantic were not conducive to additional development, but obviously very good observation. Yeah, after Ida, I believe things really slowed down.
Here's two related to the western part of the country. David and Gail have two questions here, separate questions. David says, Southern New Mexico experienced a very high rainfall in the summer of 2021, whereas the northern part of the state was dry. Can you explain the dynamics of what happened? And then also related to the Southwest there is, can you address feedback loops in the desert Southwest and how they might affect the rest of the country? So one is about,
Wow, you're really
they're,
pulling out some hard ones here.
yeah,
Okay.
well, we figured you might be up to the task, but again,
Okay.
it may not be in your field. So,
Well, there's certainly feedback in all of weather, and it's fascinating to try to understand that and sort of pick apart, what is causing what. A lot of it is, chicken and egg, as I mentioned before, which comes first, the monsoon or the downstream drought. So one thing that was interesting about 2021 is that there was the summer of the return of the monsoon across across parts of the Southwest after, I think, at least 2 years where relatively suppressed monsoon activity. And the monsoon sets up across the Southwest typically when you have a large area of high pressure in the atmosphere, large what we call ridging aloft. Very strong heating over the terrain, and then you start to see tropical moisture stream up the Gulf of California, parts of Mexico, into that regime of very hot, but generally suppressed. It's really the terrain and the moisture in the west that drives the monsoon activity, and it can become a cyclical thing. Once you get a few thunderstorms, you have a little bit more moisture available, and perhaps you can generate a number of days of monsoon activity because the pattern doesn't change all that fast, all that quickly in the summer months. And so once it gets set up, it's pretty well established. Usually comes on in July and persists through August. Of course, you get impacts from that, such as severe storms, high winds, dust storms. The haboobs in the Southwest are all a result of monsoon thunderstorm activity. Now, how that impacts downstream weather, that's a good question. Normally, it's part of a larger scale pattern. So if you have the ridge in the western or southwestern US, you tend to have some troughing in the atmosphere, some storminess downstream, but perhaps also drier across parts of the upper Midwest, because if you visualize the wind stream across North America, you're bringing in northwesterly winds across parts of the Great Plains, upper Midwest. So monsoon activity brings storms and rainfall to parts of the Southwest, while parts of the Midwest could be dry under that pattern. So these patterns do have connections across the entire continent, but then sometimes the devil's in the details. As we know, northwest winds across the plains can actually also support what we call MCS, or mesoscale convective systems. Derechos can come about through northwest flow across the Northwest, across the Midwest. So the monsoon's a fascinating aspect of the summer atmosphere across the Southwest US that indeed does have feedback further downstream across parts of the central and maybe even the eastern US.
Greg, do you have time for a few more, or are we getting closer?
It is a busy day here.
Okay, I'm going to give you one more, and then the other
Okay.
ones maybe you can follow up with.
Sure.
CoCoRaHS
Yep.
Observer, and he
Yep.
wants to know how much of our daily efforts as we go out and measure the rainfall and other precipitation are actually used in the analysis that you guys put together, and are they beneficial?
They are absolutely, as I said at the beginning of the talk, the Citizen Observer Network is a long time tradition in this country, and the citizen scientist going hundreds of years back. Those observations are critical. We do look at those as far as our storm summaries go for big events, as far as our situational awareness in the immediate aftermath of a heavy rain event. We want to know, we look at that map at CoCoRaHS and zoom in, and it's remarkable some of the density of the observations that we have that we just wouldn't have any other way. And so we'll say some of the observations are getting into even the snowfall analysis, certainly our storm summaries that we do here from the Weather Prediction Center, and then perhaps the most important is just an awareness. We know that there's a lot of variability over relatively small spaces, and so you can go from like I was showing that picture of sunset up in Vermont. New York City is getting 8 to 9 inches of rainfall, and even into parts of New England, they were having 2, 3, 4 inches of rainfall, and 50 miles away, not a drop. So that kind of information that the CoCoRaHS observers are providing is really the only kind we got. I mean, we can look at radar, but that's remotely sensed and sometimes isn't the best as far as estimating rainfall. So ground truth is everything to the meteorologist. So thank you.
Yeah, thanks. And our observers out there that are listening to us, keep up the good work. This is great stuff you guys are doing, and it's much appreciated throughout the meteorology community. Well, Greg, thanks for taking the time out of your day. And again, this is always an event we look forward to your summary each year. It really puts a perspective on where we've been. And again, thank you for doing that. And again, appreciate it.
Thanks, Henry, and thanks to CoCoRaHS, and Happy New Year, everyone. Thanks, and we'll be back next year.
Well, folks, please join us for our next CoCoRaHS Weather Talk webinar. That'll be on March 12th. So just about 2 months from today at 1 p.m. Eastern, former Navy meteorologist and former director of the National Weather Service's Office of Observations, Tom Cuff. He's going to speak on maritime weather, oceanography, and safe navigation. So be sure to sign up for that one. We'll have that on our website shortly. And finally, before signing off today, please take that short survey that it's going to pop up on your screen. So until next time, this is Henry Regis for the rest of our CoCoRaHS team saying goodbye for now and have a great afternoon.